Okay, let us start the class. So in this, so in the last 2-3 classes, we have discussed about mostly the linear PDE problems. So the linear PDEs, in the sense that we had we have discussed different cases AX plus DUY equal to 0 case, sometimes plus CU equal to 0 or f of x comma y, etc. etc. We have discussed. So in general, this is the problem we have discussed: AX plus DUY plus CU equal to f of x comma y. This is the problem we have discussed. Okay, and then we have discussed various formulas depending on the conditions, and then we have also discussed about the characteristics. Okay, so our in all the cases, what is our ultimate aim is that we are trying to convert this problem into a ODE problem. This is a PDE problem. We are trying to convert it into an ODE problem in the sense that I am just trying to convert it into a. I'm just going to introduce a parameter family, which is depending on the parameter s. Then what I'm trying to do is I'm trying to find what is my du by ds and okay, what is my du by ds and trying to find. So in order to find du by ds, I'm just since u is a function of x of s and y of s. Okay. So if I just convert this problem into this format, what I will get is that the total. This is called the total derivative. Okay, du by ds equal to what I'm going to have is that I'm going to have du by dx into dx by ds as per the function of chain rule. Okay, as per the chain rule, you can get it, and then du by dy into dy by ds you are going to. Okay, plus if it is suppose this is having a u also is inside that. Suppose it is implicit thing, then you will have something like another du by ds also. So now what you have is that we instead of this, so it is it's not du longer, it's called dou u by dou x. Okay, so it is called dou u by dou x because u is a function of two variables. Okay, dou u by dou. So in this case, if you want to match this one, what you have is that if you want to match this one to become 0, then you match this one. So here you can have that dou u by dou x is equal to dx. Therefore dx by dx I can equate to u. Similarly dou u by dou y. So here u is that dy by dx is equal to. Same way you can do that for the rest of the thing, then you will get that. So now bring that du by ds on the other side, then you will get the remaining thing. So that means what I'm trying to do is that I'm trying to find a characteristic curve of this form, okay, dx by ds equal to a, du by ds equal to b, and du by ds equal to c format, either plus c or minus c. Okay, so this is the things which we got. Now we are going to extend this idea further for the quasi-linear PDE. Okay, so that's what we are going to do. So that's what we will do it in this lecture. So we are going to consider a similar kind of thing. So here a can be constant or b can be constant, or it can be function of x comma y. Therefore it is a linear PDE. I am just going to extend this idea for a first order quasi-linear PDEs. So in this case, what I am trying to do is that I am trying to use the same thing, whatever I did for the linear PDE. I am going to extend this idea for quasi-linear PDEs also. Let us see that. So how are we going to extend this? So what I have is that in the quasi-linear PDE, what I am going to have is that I am going to have a of x comma y comma u into ux plus b of x comma y comma u into uy equal to c of x comma y comma u. Almost similar to what we had in the linear PDE, what we are going to do. So here ABC belongs to C1 of omega. Okay, where omega is a function of x comma y comma u is going to means it is at least continuous and first term differential. Okay, so what I am going to take now, I am just going to take omega naught, which is a projection. Okay, it's a projection of omega on xy plane. Only xy plane I am going to take. Okay, the projection. Okay. So as we did in the earlier thing, what we are going to do is that the solution of suppose if I find the solution of this, that is called the integral surface. Okay. So the general definition of the integral surface is as follows. So d subset of omega naught, d subset of omega naught, and u is a function from d to r. This is a function from d to r. This is a solution of this problem one. Okay. When we are then what we are going to obtain is that we are going to obtain a surface. We are going to obtain a surface, yes, represented by, because u is a subset of omega naught is a subset of projection of omega on xy plane. That means we are sitting in the xy plane. So therefore, what you are going to have? You are going to get a u of x comma y, since it is a plane. Okay, x comma y is a plane. We are going to project it, so we are going to have some kind of surface we are going to. So this I am calling as S. So this is the surface, okay, represented by this u of x comma. Okay, this is going to represent what is the complete u of x comma y. I am just going to represent. So in the Euclidean space which I am representing, okay, in Euclidean space x comma y comma u, that is called an integral surface. The surface is called an integral surface of the to the given solution, corresponding to the solution. Okay, so that is called the integral surface. So this is definition. Now, how are we going to obtain that? Okay, so the same kind of logic what we got that. So we have a, so this one I have already explained, so I'm just quickly going through this. Okay, so the normal to the surface, okay, I'm just taking a normal to the surface at a point P of x comma y comma z. Okay, I'm just taking a point P of x comma y comma u. For this, I'm taking a normal to the surface. So that can be given as follows. How is it going to be given? This can be given as ux comma uy comma minus 1. This is going to be the normal to that normal to the surface. So I remember that is the same thing as we did it in the linear PDEs also. So in that case, what was my aim is that my aim was that dvu equal to 0. This is the fundamental idea for both the problems. Okay, we want to make dvu equal to 0. So in this case, what is your v is going to be that? V is going to become like a comma b comma minus c I get. Okay, a comma b comma c I get it because here I'm taking minus 1. So a comma b comma c. Then if you take dvu is going to become like a comma b comma c dot this one ux comma uy comma minus 1. And what you are going to get? You are going to get a ux plus b uy minus c is going to be. Okay, that is same thing. Whatever I have written. Okay, so that means if I just make dv equal to 0 the same way, dv equal to 0, automatically that is going to become like a what we are going to get is that we are going to get the solution for this one. The characteristic method of characteristic we are going to apply it here. So here this is this I called as this is the this d is called the characteristic vector. Okay, this is called the characteristic vector. Same thing. Okay, here what I am trying to do is that same thing dv equal to 0 means what I am trying to do is that this is called the total derivative of the fraction vector. What I am trying to do is that I am trying to find what is my du by ds, that I am trying to find. Okay, so du by ds usually what we can write it as I mentioned earlier. So dou e by dou x into dx by ds plus dou e by dou y into dy by ds. Okay, so here this is the total derivative, or this can be written this way dv equal to. Now what you have is that you have this one du by ds equal to this one. So that means you just equate these two. So this is nothing but ux, this is nothing but uy. Therefore dx by ds I can equate with this one. Okay, dy by ds I can equate this one. Okay, so this can be written as dx by ds, and this can be written as dy by ds, and this I call it as du by ds. Okay, so that's what I am equating all these things. So that means what I am going to do is that I got to find a characteristic curve which is going to satisfy this characteristic system. Okay, suppose we have a characteristic curve. Okay, let me have a characteristic curve. The characteristic curve I denote as gamma. Gamma is nothing but x equal to x of s, y equal to y of s, u equal to u of s. This I have as a characteristic curve. Suppose it is defined. Then what we have, according to this one, we have a characteristic system. Okay, as we did in the linear P, we are going to have a characteristic system. So that is going to give dx by ds equal to a of x comma y comma u, dy by ds equal to b of x comma y comma u, dy by dx equal to c of x comma y comma u. So this is called the characteristic system. If we solve this problem, okay, if you solve this ODE problem, okay, if you solve this ODE problem, what you are going to have is that you are going to have a solution for this. Whether the solution is going to exist or not, that is going to depend on this one. Since ABC belongs to C1 of omega, what we can say is that by the existence of uniqueness theorem of ODEs for a given point, because you have taken a point P, right? So suppose a point is given, P naught is a point given, then this characteristic curve, okay, passes through exactly one characteristic curve. That is guaranteed because of the existence of uniqueness theorem of ODEs. Okay, these things we have already discussed in the previous class. I am just repeating it. Okay, so this is called the solution of the characteristic system. So once we solve this problem, we are going to get a solution for this ODE problem. that ODE is going to give you the solution for your PDE curve. Okay, that's what we okay. So this characteristic equation, okay, this characteristic equation dx by ds equal to a of x comma y, dy by dx equal to v of x comma y comma u, du by ds equal to c of x comma y comma u, that is also called as Monge's equation. Okay, that is also called as Monge's equation. Next one, that is Mange curve. Okay, so the Mange curve is nothing but, suppose this Monge's equation, you have a solution, right? You have a solution for this Monge's equation. Now, what you are going to have here? You are going to have a two-parameter family of curves in V of x comma y, because here x of s and y of s x of s and y of s is going to come. Okay, x of s and y of s is going to come. Therefore, for each s you are going to have a x of s and y of s that is going to describe some curve in the curve in the space, because for each s we will have a, okay, suppose this is my s, so this is my s and this is my s, okay, this is my x, okay. So for each s I will be having a curve. Okay, this is one curve. Similarly, for each s I will be having a curve in y also. Okay, suppose this is y and this is x and this is x, so s and x and s and y. So two parameter family of curves will come in this space. So that is called Monge's curve. Okay, so we are going to get a two family of curves, two parameter family of curves, s comma y, because this is going to come. For each s you are going to get a x and for each s you are going to get a y. So that is called the two parameter family of curves. So that is going to be tracing this surface. Okay, so for fixed x, I'll be filling all the x, then the one part will be filled. Similarly, for each y, I'll be filling another curve. So that is going to give you the another curve. So that is going to give you some kind of two parameter family of curves in this x comma y comma space, u comma space you are going to. So that is called Mange curves. Okay, that is called the Mange curve. Now, if you projection of the Mange curve, okay, the projection of the Mange curve on the xy plane, this is going to give you the curve in the xy, means in the s space. Okay, that means x comma y comma u space you are going to get the Mange curve. Now, if you project this surface on this plane, in this plane, if you are projecting it, then that parameter, two parameter family, is going to give you a characteristic. Okay, that two parameter family of characteristic curve is the projection of x comma y comma projection of the Mange curve and xy plane are called two parameter family of characteristic curves. Then this characteristic direction a comma b comma c. Okay, this a comma b comma c I have taken, right? That is called Monge's direction. The characteristic direction a comma b comma c is called Monge's direction. Okay. So this is the Mange. It is due to Caspar Mange. He is known as the father of differential geometry. It is called the father. So this is one of the important concept or the basic concept in the differential geometry, where immediately they will start with this kind of Mange curves only in the differential geometry, and one of the basic concepts in differential geometry. If you want to know more about that, you can attend some of the differential geometry courses. Okay, that will help. Okay. Now next one, a theorem. Okay. So this theorem also I have briefed you last time, but I'll just if you have any doubts on this one, I have given you as an exercise to you. Not exercise, actually I asked you to go through it once and then check it whether you have any doubts or not. So if you have any doubts in this one, you can ask now. Okay. So what I have is that I have a characteristic of gamma naught, which is nothing but I can give it as x equal to x naught of s, y equal to y naught of s, and u equal to u naught of s belongs to. Okay. So I have an integral surface. Okay. I have an integral surface. This is that. Now this gamma naught, okay, it is going to intersect with this integral surface. So gamma naught is something I have like this. Okay, I have a characteristic. This is going to intersect at the s. Okay, this is going to suppose what in this theorem what we are trying to do is that. So this gamma naught, suppose this is my gamma naught. Okay, so it is intersecting at the point. Okay, so suppose I have a integral surface. Let us say this is the integral surface. This is the, okay, and I have a gamma naught here. This is nothing but my gamma naught surface. This is intersecting only at this point. Okay, at the point I call it as p of x naught comma y naught comma u naught. Okay, this belongs to omega, and u is a function from D to R, where u belongs to C1 of D. Then what I'm saying, what this theorem is going to say is that then this gamma naught is not only intersecting, it will be something like this. Okay, this gamma naught is completely a subset of the surface. It is not just a curve which is passing through this point. It is going to, if it is intersecting here and satisfy this condition at the point x naught comma y naught comma y naught and u belongs to D of omega, D subset of R, and u is C1 of D function, then this theorem is guaranteeing is that it not only intersect this surface at this point, okay, that the entire gamma naught which is determined by this one is going to be lying in this surface itself. That means, what does it mean? So if we are saying like u is just having a this gamma naught, okay, this gamma naught condition is going to be satisfied at one point, then what it is going to say is that not only that, it is going to satisfy all these things. U naught of s is going to become like u of x naught of s for all s, okay, for all s, y naught of s is that is also okay for all s. Not only at this point, it is going to satisfy at all s. Okay, so let us see that. So this theorem I have already proved in the last but one class, I think. Any doubts on this theorem, let me know. Okay, any doubts on this theorem, let me know, because I'm just going to that. I'm going to skip this one because I already explained this one. Okay, any doubts? Have you gone through this? Any doubts on this one? Any doubts? So here we are doing this one. So u of s equal to, I'm just defining u naught of s minus u of x naught of s, y naught of s. I'm defining. So what I need to claim is that I got to claim that u of s equal to 0. So that means I got to prove this one. Okay, this is the one I got to prove. So if I prove u of s equal to 0, identically 0, then u naught of s equal to u of x naught comma s comma y naught of s for all s belongs to I will come. Okay. So you can select some s arbitrarily and then verify that. So what you need to find is that we need to find what is your du by ds. Okay, so du by ds you find it. Okay, so that you are going to calculate obtain as f of s comma u. Okay, and then use the initial condition. Use the initial condition. Okay, at the initial condition you can prove that. At the initial condition you can prove that this is going to become like u of s naught is going to become 0. Okay, u of s naught is going to become 0. That is my initial condition. Since u of s naught equal to 0 and a, b, c are continuously differentiable, what we are going to have is that according to the existential uniqueness theorem, etc., in the ODE problem, what you are going to have is that you are going to have u is identically equal to 0. That means this is going to be. Okay. So if you have any doubts on this one, let me know. Otherwise, I'll go to the next one. Any doubts? Any questions? Okay, fine. So next one more theorem. Okay, these are all I will leave it as an exercise to you. So based on the previous theorem, what we can prove is that we can prove that suppose D is a subset of omega naught, okay, and S is a surface which is determined by u equal to u of x comma y, which is an integral surface, okay, in R cube. This is a surface in R cube, okay. Then u is a function from D to R, okay, which is given, and u belongs to C1 of D, continuously differentiable. Then the following two statements are equal. What is the following two statement? So S is an integral surface of equation 1, okay. Then the surface, this is statement number 1. Statement number 2 is that yes, the surface S is union of characteristic, okay, this is our set of all union, okay, set of all union of characteristic curves of equation 1, okay. So S equal to union of characteristic curves of the equation 1. What is the equation 1? Equation 1 is this one, b of x comma y comma u into ux plus b of x comma y comma u into uy equal to c of x comma y comma. This is the equation number 4. Okay. So S is an integral surface of 1 implies that S is equal to union of characteristic curves of 1. Similarly, if S is the union of characteristic curves of 1, that implies that S is an integral surface of the equation. Okay, so that is the. So as a corollary, suppose S1 and S2 are two integral surfaces. Okay, such that what we have is that P, there is a common point. So B belongs to S1 intersection S2. There is a point which is belonging to both of the things. Okay, then some part of the characteristic curve passing through P lies on both S1 and S2. So suppose there is a point P. I have two surfaces. This is S1, and I have another surface. Let's say S2. Okay, so this is S2. So I have two surfaces. Now what I have is that suppose there is a point. Okay, there is a point P which is belonging to S1 intersection S2. Then I have already shown that. So S1 is the integral surface which is a union of characteristic curve. Okay, so that means some part of the characteristic curve. You take any characteristic curve. Okay, some part of the characteristic curve. P belongs to S1 intersection S2. Then what it is going to say? Some part of the characteristic curves passing through this P. Okay, suppose there is a characteristic curve passing through P, then that will be lying on both. It will be lying in S1 as well as in S2. It is going to be. Okay, that is the because it is saying the surface S is the union of characteristic curve. So from that we can obtain this curve. Next one, if two integral surfaces intersect without touching and intersection in a curve. Okay, suppose two integral surfaces intersect without touching. Okay, without touching they are intersecting. Okay, two integral surfaces they are intersecting without touching, and the intersection in a curve. Okay, that is the intersection in a curve. There's a curve there. Without touching they are intersecting in a curve. Intersecting in a curve. Now what it is going to do? Then this gamma is a characteristic curve. These are all the corollaries for this theorem. So this I will be leaving it as an exercise because this is straightforward from the previous theorem. From this theorem you can obtain this exercise. This I will just leave it to you as an exercise. So you can prove theorem. What you need to prove is that 1 implies 2 follows from theorem 1. Okay, because here already we have proved that if you take any integral surface and if you take any part, automatically that gamma naught is going to be subset of S. So that means we take any characteristic curve. If S is an integral surface, we take any characteristic curve that is going to be again as a part of this one. That means we take union of all characteristic curve is going to come. Okay, so that is following from theorem 1, very straightforward. The first answer is very straightforward. 2 implies 1, you have to prove it. That is little tricky because union of characteristic curve, then you have to prove it. That is second part is little. Then using that you can prove corollary 1 and corollary. So I'm not going to give the proofs, you can just prove as an exercise. Okay. So one more theorem for this existence and uniqueness, because using this only we have solved some problems in the linear PDEs also, and we'll be solving some problems in the next today after the theorem is proved. Okay, so that is also. So in this theorem, the next theorem also I will leave a small portion to you to explore and prove it. Okay, so I'll just leave one part of the theorem to prove by you. Remaining part I will prove it. Okay, so this is a theorem from Rudy. Okay, so have you seen this theorem? Anyone in this Rudy? I mean the second course, method theory and multivariable calculus course. Have you seen this theorem? Inverse function theorem?
Yes, sir.
Yeah. So that is the fundamental thing for our for this quasi-linear PDE to get a answer with existence uniqueness for this PDE theorem. Okay. So existence we have already proved. For uniqueness we require this. Okay, this will be used for the existence uniqueness theorem for quasi. So this theorem you might have seen already. So F is a C1 function. Suppose F is a C1 function. Okay, C1 mapping of an open set E subset of R power n. Okay. F dash of A is and other things. So F dash of suppose A is a point. Okay. F dash of A is invertible. It is invertible for some A in. Okay, and it is given that B equal to F of T. So these are all given. Then what this theorem is guaranteeing is that there exists open sets. Okay, there exists open sets U, okay, and V in R power n. U and V in R power n, such that A belongs to U, okay, and B belongs to V, okay, and F is 1 1. F is 1 1 on U. F is 1 1 on U. That is and F of U equal to B. Okay, this is first part. Second part is that if G is the inverse of F. Okay, G is inverse of F. Okay, inverse of F. Okay, defined by defined in B. Okay, it is defined in B because D is inverse of F. Since B equal to F, I'm just defining it in B. Defined in B such that G of F of X equal to X, where X belongs to. Okay, then G is in C1 of B. F is in C1 of F is a C1 mapping. Okay, so that means it is in C1 of. Okay, therefore G belongs to C1 of. So this theorem you might have studied and proved in the earlier semester. So now we are going to rewrite this theorem for R square. Okay, that is going to be helpful for our existence of uniqueness theorem for possibility. So let us rewrite this theorem in R power R square. Okay. So what I am going to take is that I am going to take a part. So here A belongs to I am taking A belongs to E, right? So here what I am going to take is that I am going to take P naught. Okay, in the place of A I am going to take P naught, which is going to be S naught comma T naught. Okay, two parameter. Okay, so it belongs to D, which is a subset of R square. Which is a subset of R square. Okay. So here I am just denoting S comma T. That means it is the variables are S and T. Okay, R square, that variables are S and T. Similarly, I am just going to denote Q naught of X naught comma Y naught. Okay, which is belonging to D dash subset of R X comma Y square. Which means here I am just going to denote the variables as X and Y. Okay, same thing. So here A belongs to E and B belongs to K. The part here is there, right? So here in the place of U, I'm just taking D. In the place of E, I'm taking D dash. Okay. So here I'm saying A. So here, since it is a two parameter, I'm just saying S naught comma T naught or S comma T and X comma Y. I'm just taking. Now in the place of F, what I'm going to take is that I'm just going to take a mapping pi. Okay, which is from D to D dash. Here I'm taking U to V. Okay. So same way I'm just taking D to D dash. Okay, then and I'm just taking pi belongs to C1 of, because F is a C1 mapping, right? So I'm just taking pi belongs to C1. And it is given that B equal to F of A. So in that case, I'm just writing this pi of P naught equal to P naught. Okay, so I can just map it similar to this. Wherever A is there, P naught, wherever B is there, okay, pi of P naught equal to P naught. So that means what I'm having, pi is such that X equal to X of S comma T, because in pi belongs to pi is a mapping from T to D dash. In T dash the variables are X and Y. Therefore, whatever variable there, it can be written as X. In the domain is S comma T is the variable, so X can be written as X of S comma T. Similarly, Y can be written as Y of S comma T. Okay. And what I have, okay, so this it is having the 1 1 mapping, right? So for this part we are going to have that we are going to have a Jacobian J pi of P naught, which is a Jacobian. So Jacobian is going to be dou of X comma Y divided by dou of X comma T, okay, of P naught, which can be written as X naught excess of P naught. Excess means I'm taking the derivative of X with respect to the variable S, okay, into Y T of P naught. That means I'm taking derivative of Y with respect to the variable T, okay, minus xt of P naught into Y Ys of P naught, which I am assuming not. This is not equal to 0, automatically this is going to be F is 1. Okay. So then what is it going to say? So here we have taken some neighbor u subset of open set without taken, right? So in this case we are going to take a neighborhood. So open set u, I'm going to take in the place of open set, I'm going to take neighborhood u. Okay, open there is a neighborhood u of p naught, in B. Okay, so some local neighborhood I'm going to take. Similarly, in the place of p, I'm going to take b. Okay, b naught is a neighborhood of p naught, q naught, not p naught, q naught in D dash. Okay, p naught is the neighborhood of u is the neighborhood of p naught in D. D naught is the neighborhood of q naught in D dash. Okay, so that is a neighborhood, and the mapping is I will be having a mapping also. Pi inverse is going to be existing. Okay, pi inverse is going to be in C1 of u is going to be there as I have here. Okay, so here G is the inverse, means G belongs to G1 of D was the right. Pi belongs to C1 of u dash. Okay, so u dash is going to be there, or sorry, here not D dash. I confused here. So I'm just D dash, right? So I'm just going to C1 of u dash. Okay, pi inverse belongs to C1 of u dash is going to be there. So this u dash is similar to this. Okay, u is as it is u dash is nothing but as it is. Okay, so u dash is a neighborhood of q naught D dash. That means pi inverse belongs to C inverse of u dash, which is from this one equivalently this one, and I have pi inverse of u. Okay, pi inverse of u is going to be pi inverse of u dash is going to be, okay, pi inverse of u dash is going to be. Okay, and further one more thing. Okay, j pi inverse of q naught is going to be j pi p naught whole inverse. Okay, so that is good. J pi q inverse j pi inverse of q naught is going to be j pi p inverse. So all these things because of this theorem. Okay, these two things I am just using it over here, and then I am applying it. Okay, this is the inverse mapping theorem in two variables, which is going to be useful for us. Okay, so this is the fact we are going to use it. Mainly this concept we are going to use it in our theorem. Okay, mainly this concept we are going to use it. Of course, this is also going to be giving you the existence of uniqueness. So this is the major concept. Okay, the important concept which is Jacobian contributed. That is the major thing which we are going to use it, and then we are going to obtain the unique solution for the quasi-linear theorem. Okay, so you can just map it both of things. Okay, the two r square thing and r power n thing. Any questions? Okay, fine. So next one, let us go for existence of uniqueness theorem for the quasi-linear PDE. So let us consider this PDE once again. A of x comma y comma u into ux is b of x comma y comma u into uy equal to c of x comma y comma u. Okay, let us consider this theorem. Consider this quasi-linear PDE. Okay, and the ABC belongs to C1 of omega. Okay, and I'm defining this gamma. Gamma is nothing but x equal to x naught of s, y equal to y naught of s, and u equal to u naught of s. This is key. So in this problem, I'm going to stick to s belongs to 0, 1 for g. We are not going to take it other thing. You can transform that. Okay, if it is s belongs to 0, 1, you can, wherever you want, you can just transform the problem to that respective domain. Okay, using that. So suppose if I define it for 0, 1, automatically you can define it for some a comma b also you can define. Okay, that mapping is using the composition you can. Okay, so I'm going to consider only s belongs to 0, 1, which can extend it further. So this is an initial smooth curve in omega. Okay, and this condition is satisfied. Dx naught by ds into d of x naught of s comma y naught of s comma u naught of s minus d y naught of s divided by a of x naught of s comma y naught of s comma u naught of s is not equal to. Okay, so this is called the transversality condition. We'll see it. Okay, so these conditions are satisfied. This is the given PDE, and gamma is an initial smooth curve, and this is not equal to. Okay, if this is not equal to 0, then what this theorem is going to guarantee is that there exists at most one solution. There exists at most one solution. U equal to u of x comma y. Okay, that is at most one solution. That means unique solution. Define a neighborhood of this initial curve. This is the initial curve. Define an initial neighborhood of this initial curve. Satisfies this equation 1. Okay, and the initial condition that u naught of s equal to u of x naught of s, comma y naught of s, belongs to 0. This is the initial condition. Okay. So if these two conditions are satisfied, there is a unique solution u equal to u of x comma y, which satisfies equation 1 as well as this initial condition u equal to u of x naught of s comma y naught of s. So let us prove this. I'll prove 2 lines of the proof without explanation, which is very straightforward actually, but just request you to go through it once again. The remaining part I'll do. So as we have for this problem, what is the Cauchy problem, or what is the characteristic system is going to be there. So the characteristic system is that C I am just defining. Okay, it is going to be dx by ds equal to a of x comma y comma u. dy by ds is going to become like d of x comma y comma u, and du by ds equal to c of x comma y comma u. This is the characteristic system or the Cauchy problem of the ODE system. So I'm going to take the initial conditions for this one because it is the 2-parameter family curve. I'm going to take it. Okay, so how am I going to use that? Because I'm going to use the inverse mapping theorem, which I have explained earlier. That's what I'm going to take it. So I'm going to define something like x equal to x of x comma t and y equal to y of x comma t, etc. I'm going to define. So with initial condition, I'm going to take as follows. Okay, for this problem, I'm going to take this initial condition x naught x of x comma 0 equal to x naught of s. I'm going to take it. Okay, y of x comma 0 equal to y naught of s, and u of s comma 0 equal to u naught of s. Okay, so this is the characteristic system with initial condition I have to. Then from the existence of uniqueness theorem of the ODEs, what we can guarantee is that there is a unique solution for this problem. Okay, this unique solution is going to obtain as follows: x of s comma t. Okay, x equal to x of s comma t, y equal to y of s comma t, and u equal to u of s comma t. Okay, remember that here I'm just denoting x of s comma 0 equal to x naught of s, y of s comma 0 equal to y naught of s, u of s comma 0 equal to u naught of s. Therefore, only this place I'm going to have a variables over there. This is going to be set only x of s comma t over s comma t. Where t is going to belong to, okay, some alpha of s comma beta of this is going to be. What is alpha s comma beta s? So they have some continuous function. Their alpha and beta are some continuous function here. Means I'm just solving this problem, okay, because we are going to have this problem to be satisfied in some condition. Okay, because here a of x comma y comma u s belongs to 0 comma 1 is that what you will be obtaining is that you will be obtaining some kind of using the existence of uniqueness theorem. You will not get everything from s belongs to 0 comma 1. Maybe you will be having some subinterval. In the subinterval only it may be. So those subinterval, it is going to become like alpha s comma beta. Okay. Now I'm going to define a set called, I have to use the inverse mapping theorem. For this I'm just defining a D. Okay, D is nothing but set of all s comma t such that s belongs to 0 comma 1 and t belongs to alpha of s comma beta of s. Okay. This is a subset of omega s. Okay. Now D is the, I'm just going to take D is the projection of xy plane. Okay, D is the projection of xy plane. Okay, so that we have. Now we define pi. Okay, pi, we define pi. So inverse as in inverse mapping theorem. Okay, as in inverse mapping theorem means you got to define like this. So like this you got to define pi. Pi equal to x equal to x of s comma t, y equal to y of s. Okay, that I am defining. Okay. And then what you are going to have as per the inverse mapping theorem, what you are going to have is that j pi at t equal to 0. Okay, so that is going to become like dx naught by ds. To see that here. Okay, dx naught by ds, because excess is there, so that is nothing but dx naught by ds is going to come. Okay, into b is going to come. Okay, minus dy naught by ds into a is going to come. This one. Okay, also pi is in inverse mapping theorem. What you are going to have dx naught by ds into b minus dy naught by ds into a is not equal to 0. Okay, so this is the okay. So this one we have. Now what you have is that okay. What you have here is that you have by inverse mapping theorem, you have a unique, you have a inverse mapping. The inverse mapping is going to come like pi inverse. Okay, the pi inverse is going to be there as follows. So s equal to, so this is defined as follows: s equal to s of x comma y and t equal to t of x comma y. So this is to be defined in a neighborhood of gamma dash. This is my gamma. Okay. So now I am going to have a inverse mapping. That means I am going to have it on the other side also. I have to define what is that. Okay. So that is going to give you. This is going to define in a neighborhood of. Okay, in a neighborhood of n dash. The neighborhood n dash of gamma dash. Okay. So I have used this one, obtain the solution using the existence of uniqueness theorem. I'm defining the set E. Then from that, and this is therefore this is not equal to 0. If it is not equal to 0, again you can use the inverse mapping theorem. As per that, pi inverse is going to exist, and that is going to satisfy this. Okay. In some neighborhood, as per that inverse mapping theorem, it was given there is a neighborhood U of P naught and U dash of Q naught was there. Same thing here. I'm just going to take because that P naught was some initial point. So here the initial point is this one. It's not always one out of this. Okay, so some initial point was there. So for this one, if you take the neighborhood is going to be, suppose if I take a neighborhood of n here, then correspondingly there will be a neighborhood of n dash in the other side also. So n dash of gamma dash is here. Okay. Now what we are going to do? Now next part. So almost we are done. Okay, so only this part I will be leaving it to you. Part of your exercise. So now what you define, u is equal to u of x of x comma y comma t of x comma y. Okay, because u is a function of x comma u of x comma t, which we have. So but now s equal to s of x comma y and t equal to t of x comma y. Okay. So this is going to be, I just define a small pi of x now. Okay, this is capital pi. Okay, this is small pi of x now. Now I am trying to find what is a pi x plus b pi. What is this? Okay, pi is nothing but u of x comma y and t of x comma y. So this is going to be a into u. So pi x is nothing but u s into sx. Okay, because using the change, and then plus u t tx. Okay, similarly plus b into u s sy plus u t ty is. Okay, now take us common. So if you take us common, this is going to become like asx plus bsy plus ut is going to become like atx plus bty is going to come. Now I will leave it to you as an exercise. What you have to check is that okay. Now what else I have is that as per the characteristic system. Okay, as per the characteristic system, dx by dt. No. Yes, x is there. Yeah. Us is there. Us is there. A is there. Yeah. A is there. Okay. Now a. What is a here? A is nothing but dx by dt. So therefore this one I can write as us into xt sx. Okay. B is nothing but dy by dt. Therefore this is going to become like u is nothing but yt sy. Similarly, ut into xt tx plus yt ty. Now I leave it to you as an exercise. What you got to prove is that xt into sx plus yt into sy equal to 0. This one you got to prove. Then second part is that xt into tx plus yt into ty equal to 1. Okay. So this part I will leave it to you as an exercise. Check it. Okay. Then if it is there, okay, so this is going to be there. Then what you are going to set, you are going to get. So this part is exercise. So us into 0 plus ut into 1 is going to come. What is ut? As per this one, ut is nothing but c. Therefore, this is going to be c. So what you obtain? A pi x plus p pi y equal to c is going to be. Okay, a pi x plus p pi y is going to be. Okay. Now what else I have? One more condition is that phi of u equal to u of s of x comma y, d of x comma y. Therefore, from this one, what is phi of x naught of s comma y naught of s is going to be. Okay. So that is going to be u of s of x naught of s comma y naught of s. Sorry, x naught of x naught of s comma y naught of s. Okay. Similarly, key of x naught of s comma y naught of s. Okay. So that is nothing but u of s comma g. Okay. That is nothing but u naught of s. Okay, because t is not there, right? So u of s comma t is there. Here everything is going to be in terms of s only. Therefore, it is going to come with u of s comma g. T is not there. So u of s comma g is going to be there. And u naught of s is going to be. This is nothing but u naught of s. So from this one, what we are going to obtain is that, okay, now what we are going to prove that we are going to prove the we have already proved the existence. Okay, this one existence already we have proved. Now we are trying to prove the uniqueness only. Okay, so how are we going to prove the uniqueness? So it is satisfying two conditions. Okay, this phi is going to satisfy two conditions. One is a pi x plus p pi y equal to c. That means the original is satisfying this phi. And then it is satisfying this initial condition of phi of x naught of s y naught of s equal to u naught of s. Okay, phi of x naught of s y naught of s u naught of s is complete. That means it is satisfying this completely. Okay, one as well as this one. Together it is satisfying. Now what we need to prove is that using this one, we got to prove that the solution is going to be unique. So that's what we are going to do. Okay. Suppose once we try to prove, okay, in most of the cases, what we do is that suppose there are two distinct solutions are there. What we need to prove that both are either we need to prove that it's a contradiction, or you got to prove that both are same. Okay. Suppose two solutions are there, you got to prove both are same. Okay, that's what we are doing. So let us consider phi 1 and phi 2 are two solutions. Okay. So what I got this one. A pi x plus b pi y equal to c is there, and it is satisfying this one. Phi of x naught of s comma y naught of s is nothing but u naught of s. So this is there. Okay. Now suppose phi 1 and phi 2 are two distinct solutions. Phi 1 and phi 2 are distinct. Two distinct solutions. Okay. Of this equation, satisfying the initial conditions. And what you have? So you are going to have a two integral surfaces we are going to take. Okay, S1 be the corresponding integral surface for phi 1, and S2 is the integral surface corresponding to phi 2. Okay, so S1 and S2 are two corresponding surfaces. Therefore, what we are going to have? We are going to have two system of ODEs we are going to take. One is nothing but because it's the integral surface, it has to satisfy the characteristic system. Okay, so dx by dt equal to a of x comma y comma phi 1 of x comma y. Okay, that is one thing. And phi of x comma 0 equal to x of x comma 0 equal to x of s comma 0 equal to x naught of s. Okay, and dy by dt equal to b of x comma y comma phi 2 of x comma y of x comma 0 equal to y naught of s. Okay, this is by s1. Okay, this is by s1. Similarly, s2 I can do the same thing. Dx by dt equal to a of x comma y comma u y comma pi 2 of x comma y. Okay, same thing. Okay, then dy by dt equal to d of x comma y comma pi 2 of x comma y. Okay, same thing. Y of x comma equal to 1. So that means we found two solutions. Okay, one is nothing but, so for this problem, what we are going to have is that you are going to have two solutions. One is x1 of s comma t, comma y1 of s comma t. That is one solution for the first one. Okay. Then we have x2 of s comma t, comma y2 of s comma t. That is corresponding to this one. Okay. So two solutions are there. Therefore, what we are going to have? We are going to have x1 of s comma t and y1 of s comma t and x2 of s comma t, y2 of s comma t, comma y2 of s comma t are going to be the solution for this characteristic system. Means for the Cauchy linear PD. With this Cauchy problem, there are two solutions you are going to get. Okay, but what we have as per the uniqueness theorem of ODE is what we are going to have. We are going to have only one solution because the uniqueness theorem. What we are going to have? We are going to have only one solution is going to be there. Okay, but what we are claiming here is that since x1 of s comma t, y1 of s comma t are two solutions of this characteristic ODE, okay, this characteristic system, automatically s1 of s comma t and y1 of s comma t, comma y1 of s comma t is a solution of this problem. Again, x2 of s comma t, y2 of s comma t, and y2 of s comma t is also going to be another solution. Since these two are distinct solutions, y1 and y2 are distinct, automatically the solution for this system is also going to be distinct. That means we are going to have two solutions for this one, which is not correct because we have uniqueness theorem. Okay, by uniqueness theorem, what you are going to have? In this case, both should be same. Okay, if it is two solutions you obtain, then both solutions will be same. Okay, therefore, by the uniqueness theorem of ODE is both x1 of s comma t and y1 of s comma t and y1 of x comma t and x2 of s comma t, y2 of s comma t and y2 of s comma t both should coincide in the common domain of their definition. It should be coincide. So that means if you have two curves, two characteristic curves, you have both should coincide at the point p of x naught comma y naught comma u of s. Okay, so that means you obtain the that means both are same. Both are coinciding with both are same. Therefore, pi1 and pi2 cannot be distinct. They are same. That means the uniqueness theorem. So only this portion I have left it as a exercise to you. Only one part. Just explain. Okay. So this theorem states what is the theorem is stating is that in a physical sense, what it's saying. So whenever there is a theta curve, so this is a theta curve, right? So this is a theta curve. Whenever there is a theta curve, whenever the theta curve gamma, okay, the gamma is not tangential to that characteristic curve. Suppose I have a theta curve. Okay, I have a theta curve. Theta curve means whenever you have a PDE, okay, you have a PDE. For this PDE box, you have to give some input. Okay, this input you have to provide. That is, it can be initial condition or boundary condition. According to that, you will be obtaining the answer. So this input I give it as a data curve. Okay, whenever there is a data curve which is not tangential to the characteristic curve. So suppose I have a characteristic curve for which it is not tangential to that characteristic curve. Okay, then what is it going to say? The solution, the existence of the solution is going to be unique. So how that is going to be saying? Because this condition, see this one, whenever you have a dx by dt and dy by dt, that is going to say about the what is the dx by dt in the ODE case. ODE case it is tangents, right? So in this case, it is going to be a once you obtain this characteristic curve, suppose it is not tangential. If it is not tangential to that, then automatically you are going to have these conditions are satisfied. Okay, this not equal to 0 conditions are going to be satisfied. If it is tangential, you will be getting 0 over. If it is not tangential, you are going to get not equal to 0. Therefore, you are going to get the answer as unique solution. Okay, that's what it is going to say. Okay, so both conditions should be there. It is not, the data curve is not tangential to the characteristic curve, and the functions ABC belongs to C1 of omega, then the solution is going to be existing. So as I mentioned earlier, this condition T of S, okay, or dx naught by ds into B, okay, minus dy naught by ds into dx naught, that is called transversality condition. Okay, not equal to 0, that is called the transversality condition. Okay, there is a geometrical interpretation also. So the geometrical interpretation of this theorem is that, so the projection, okay, the projection of the characteristic curves in the xy plane, okay, suppose there is a projection of the characteristic curve in the xy plane, and that passes through this one x naught of s, y naught of s, and u naught of s, okay, that intersects the projection of the initial curve gamma non-tangential. Okay, that is the geometrical interpretation. So its uniqueness is going to be that we have a projection of this characteristic curve in the xy plane that is going to intersect the projection of the initial curve non-tangential. If it is intersecting tangentially, automatically the transversality condition is going to be 0. Okay, if it is intersecting tangentially, intersecting the initial curve tangentially, that is going to be 0. Otherwise, it is not going to be. So what will happen if this condition fails? Okay, suppose this d of s is equal to 0, then automatically neither existence nor uniqueness is given. Let us see that with exercise. Okay, so let us see 2 exercise problem, and then we will complete the class. So you have yux minus xuy equal to 0. With initial curve gamma is nothing but x equal to x naught of s equal to s, y equal to y naught of s equal to 0, u equal to u naught of s equal to s. Okay, so what you got to prove is that you have a you got to prove it has a unique solution. Let us prove that. So what is the characteristic equation? Dx by dt equal to a, which is y, dy by dt equal to b, which is minus x, and du by dt, which is nothing but 0. Because it is 0. So let us solve this problem. Okay. So if you solve this dx by dt and dy by dt, what you are going to get? You are going to get from this one, you can get dy by dx equal to minus y by x, minus x by y. So which implies you can solve this problem, you are going to get x square plus y square equal to c. Okay, some constant is going to x square plus y square equal to c square. So therefore, your characteristic curves are circles. The characteristic curves are circles with center 0, 0. Okay, and therefore the general solution is going to become like q of x, y is going to become like f of x square plus y square. Okay, the general solution is going to be of the form u of x, y equal to f of x square, y square. Now we got to prove the uniqueness. Okay, so it is given that x naught equal to s and y naught equal to 0 and u naught equal to s square. So therefore, I am just going to substitute it over here. So what we are going to get is that u equal to so from here you can see that u equal to s square. Okay, if I put s equal to x, this is going to become x square. Therefore, u equal to x square. This is nothing but parabola. Okay, it is going to be a parabola. Okay, it is going to be a parabola. U equal to x square, comma y is 0 here. Okay, so this is going to be a parabola in the xu plane. Y equal to x square, comma y equal to 0 is a parabola in the xu plane. Okay, now transversality condition. What is the transversality condition? P of s, which is nothing but dx naught by ds into b of x naught, comma y naught, comma u naught. Okay, minus dy naught by ds into a of x naught, comma y naught, comma u naught. Okay, what is dx naught by ds? Which is nothing but s, so it is going to be 1. Okay, and what is b of x naught, comma y naught, comma u naught? So that is going to be b is nothing but minus x. Okay, so that is going to be there. So minus s is going to be there. So minus s is going to be coming here. Okay, minus dy naught by ds. Y is already 0, therefore this is 0, so it is not going to be there. So minus s is going to come, so it is not equal to 0. Okay, so t of s is not equal to 0. That means, as per the previous theorem, you are going to have a unique solution is going to come. Okay, so therefore, what you are going to get? Sorry. So therefore, what you are going to get is that here from this one, u equal to x square is there, right? Okay, and here what you have, u of x, y is going to be f of x square plus y square. Okay, according to this initial condition, x equal to x s and y equal to 0. What you are going to get is that you are going to have u is going to become like, for this one, this is going to become like s square. This is going to become like f of x square. X square is nothing but s square plus y is 0, so this is going to be f of x square. So that means f of x square equal to f square means f is nothing but f of x equal to x. That means it is identity. Okay, it is identity. Therefore, what you are going to get? You are going to get u of x comma y equal to x square plus y. So this is your solution. Therefore, u equal to x square plus y square is a circular parabola. You are going to get a circular parabola. You are going to get. Okay, so it is going to be like this. So you take a family of all these things. Okay, so that is nothing but your solution. Okay, next problem. One more problem. You complete. Same thing. I am just changing the condition. So this is going to become a cos s, and this is going to become a sin s, and this is going to become like sines. Okay, same thing. These are all same. These are all same. Only the transvality condition is going to change. Okay, the transvality condition, and this part is going to change. Okay. So this is going to be same. U equal to f of x square plus y square because I did not change the problem. Only the condition I have changed. So now what you are going to have is that you are going to find what is the t of s with t of s is nothing but dx naught by ds, which is going to become like minus sin s. Okay, minus sin s, and into b naught. So b naught is minus x. Okay, so minus x is nothing but the cos s. So it is going to become like plus cos s. Okay, and minus dy naught by ds is going to become like cos s. Okay, into a naught is y is sin s. Okay, cos s into sin s. So sin s cos s sin s, they both are getting cancelled. So 0 is 1. So that means you cannot guarantee whether the solution is going to exist or uniqueness is going to be guaranteed. Okay, so let us see that. So the initial curve, for the initial curve, you can see that x square plus y square equal to, because cos square s plus sin square s equal to 1. Okay, and u equal to, you can see that u equal to 1. The initial curve, this is going to be there. Okay, so if u equal to x square equal u equal to, suppose u equal to f of x square plus y square is a solution. Okay, solution. Then on the circle, then on the circle x square plus y square equal to 1. What you are going to obtain is that you are going to obtain u equal to f of 1. You are going to obtain. Okay, but that means you are going to obtain a constant. F of 1 means it is going to be a constant. But what I got, u equal to y is going to be there. Okay, this is a contradiction. Okay, one side I got u equal to f of 1, another side I got u equal to 1. So here it is a constant, here it is a variable. That means there is no solution for it exist. Okay, one last problem. Then we will complete. Now I'm just changing this one. Instead of this, I'm just going to put it 1. Okay, so if I just put it as 1, then in this case, again the same thing. This is going to be 0. Again, same thing, 0 is going to come. So here, this is going to become like u equal to 1. That means now I'm not going to get no solution, but instead I'm going to get a unique, infinite number of solutions. Because f of 1 equal to 1 means there will be plenty of solutions will come. For example, if we take f of omega equal to omega power n, where omega is the nth root of t, then that means you are going to get infinitely many solutions. Okay, so you can take any omega power n, but n can be anything. So automatically you are going to get f of 1 equal to 1 is going to be obtained for many functions. Okay, so that means you are going to get infinitely many solutions. Okay, we obtain f of 1 equal to 1 here, so we are going to get infinitely. So this I will stop. So this I will give as an exercise. Okay, consider this following PDE with different Cauchy data. You got to find the solution for this. Okay, either because a unique solution or infinitely many solution or no solutions. Okay. So this is an exercise. Any questions? Any questions? So we have used this theorem to prove one problem. I do one more exercise. So in this problem, what you need to take is that I have given simply u of x comma 0 equal to e power cx. Okay, so in this case, I just give you the king terms of how to solve. So gamma, the same way you got to obtain. So this case x equal to, okay, x naught of s equal to first problem. Problem number 1, it will be s. Y equal to y naught of s equal to 0. U equal to u naught of s equal to, this is going to become like e power cx. That means e power cs is going to come because x equal to s, e power cs. Same thing for the second problem. It is going to become like This is going to become like, okay, so this part, this is going to become like 1, sorry, 0. This is going to become like yes, okay, and this is going to become like 0. Third problem, this is yes, this is 0, this is silence. Okay, so all these things, remaining things are same here. So ux equal to cu is there, so you have to prove it with the signal. Okay, so in this case, extra one is there. So here dx by dt. So this problem I will just keep the key also here. So dx by dt is going to become what? dy by dt is going to become 0, and du by dt is going to become c minus sorry c. Okay, and then you can solve this problem points. Okay. Any questions? Let me know. Otherwise, let me stop. Okay, thank you. Yeah, that's not your question. You asked some questions, right? Is it answered in this class? Or still you got doubts? Okay.
Yes, sir, it is clear.
Okay, thank you. Thank you.